In this short lesson, we're going to recap some of the information about intermolecular forces, and this is needed as a preamble to consider the physical properties of organic compounds. And the reason for this is that the physical properties, as we learned previously, are determined by the strength of the intermolecular forces, those forces between the organic molecules. So we're going to start by looking at what we call London or dispersion forces. Sometimes they're just called van der Waals forces. That's not entirely correct in that all intermolecular forces are often referred to as van der Waals forces, but for sake of ease, dispersion forces often are just called van der Waals forces. We've got two molecules of propane here, 3 carbon atoms bonded singly. First thing to notice is that these are symmetrical molecules. You may remember when trying to consider whether a molecule is polar or non-polar, we need to look at the bonds. The carbon-hydrogen bond is polar. Carbon has an electronegativity of 2.5 and hydrogen of 2.1. So the bond there is a polar bond. It's slightly positive on the hydrogen side and slightly negative on the carbon side, but because the propane structure is symmetrical, overall it's a non-polar molecule. But what we do need to remember, of course, is that there are a great number of electrons within this compound. Each of those bonds is made up of a shared pair of electrons, and carbon itself has got various other electrons. So there are a number of electrons kind of floating around in this particular area. And as these electrons move, at any given point, we might find that the electrons might just be slightly more to the one side of the molecule than to the other side. And if that happens, then we get a very slight, that's a delta, a Greek letter delta, meaning a very slightly negative charge on this side, which would leave a very slightly positive charge. And that might just happen instantaneously. What then happens is that due to the slight negative charge on the one side of the molecule, the next molecule, the electrons are then repelled across to the other side of the molecule slightly, meaning that this end becomes slightly negative, leaving that end slightly positive. And what we then get is a very weak interaction between the two molecules due to the slight negative and slight positive charge. The key here is that these van der Waals forces or London or dispersion forces are very weak indeed, easily broken, and that will of course impact the physical properties a little bit later on. So that's the first kind of intermolecular force. It's an instantaneous dipole that exists, which then causes a very weak interaction between the molecules. If we then go on to the next type of force, a dipole-dipole force, in this particular case, if we, let's just go back to dipole-dipole forces. There we go. If we consider the carbon-chlorine bond, carbon has an electronegativity, as we saw last time, of 2.5, chlorine of 3.0, and so chlorine attracts this shared pair of electrons here, get attracted to the chlorine, meaning that this side becomes slightly negative, that side slightly positive. And because this molecule is not symmetrical, the chlorine over there is attracting the electrons, making this side negative, and so this side of the molecule becomes negative, that side becomes positive. Similarly on this side, there's the chlorine there, so this side is negative and this side is slightly positive. Now, what happens with the dipole-dipole situation is that we have a permanent dipole setup. The chlorine constantly attracts that shared pair of electrons, so this side over here is always slightly negative, meaning this side is always slightly positive, and so the interactions that we get between those molecules, the weak intermolecular forces, are slightly stronger than with the